Hello dear students, welcome to the lecture series on geography. The ocean is part of our lives. It plays an important role in the earth environment. Many aspects of the ocean affect us. It controls climate, supports life, creates land and provides resources. Life on earth depends on the ocean. The ocean is a system of chemical, physical and biological processes. Some of these processes are driven by basic science concepts, temperature and salinity. In this regard, last episode we discussed about ocean water circulation, and now we will move on to the ocean temperature and salinity. And the topic is subdivided into the following captions. They are ocean water temperature, salinity of ocean water, temperature distribution in the ocean, salinity distribution in the ocean, and environmental considerations. Let us start with ocean water temperature. The temperature of the ocean determines what form the water takes. Most of the ocean is liquid water, but if it gets cold enough, it turns to solid ice, or if it gets hot enough, it can pass on into the atmosphere as water vapor. Water warms up more slowly than air but can hold more heat. Water needs 4 times as much energy to raise its temperature by 1 degree centigrade as the same mass of air does. So, the ocean plays an important part in taking up energy from the sun and stopping the earth getting too hot. The oceans has a wide range of temperatures from the almost 38 degrees centigrade shallow coastal waters of the tropics to the nearly freezing waters of the poles. The freezing point of seawater is about -2 degrees centigrade instead of the 0 degrees centigrade freezing point of ordinary water. Temperature and density share an inverse relationship. As temperature increases, the space between water molecules increases, also known as density, which therefore decreases. If the temperature of water decreases, its density increases, but only to a point. At the temperature of 4 degrees centigrade, pure water reaches its maximum or peak density. Cooled further, it expands and becomes less dense than the surrounding water. This is why when water freezes at 0 degrees centigrade, it floats. The ocean water is constantly churning underneath, bringing nutrients up to the top. The difference in density of cold water versus density of warmer water is responsible for ocean currents and upwelling. Warm seawater floats and cold, dense seawater sinks. So, ocean temperatures also vary across the surface and into the depths. Temperatures range from -2 degrees centigrade to 28 degrees centigrade in most cases, but are hotter near hydrothermal vents or closer to land. When the temperature, density or salinity of a layer changes rapidly, this region is referred to as cline. Thermoclines are the most important due to their effect on planktonic ecosystems and primary producers. Thermoclines occur a short distance offshore when the shallow surface water is heated by the sun, resulting in warm, less dense water staying at the surface and the sinking of cold, dense water. 2 other terms parallel to the term thermocline are used in oceanography. The halocline is the zone of rapidly changing salinity between relatively low salinity surface water and deeper, more saline waters. The pycnocline marks a zone of rapidly changing density. Next, coming to salinity of ocean water. There are many chemicals in seawater that make it salty. Most of them get there from rivers carrying chemicals dissolved out of rock and soil. The main one is sodium chloride, often just called salt. Most seawater has about 35 grams of salt in every 1000 grams of water. Salt is expensive to remove from water, and salt content is an important factor in water use. Although everyone knows that seawater is salty, few know that even small variations in ocean surface can have dramatic effects on the water cycle and ocean circulation. Throughout Earth's history, certain processes have served to make the ocean salty. Among the various physical properties of the ocean, salinity is the most vital factor besides temperature and pressure. The presence of salts in ocean water causes salinity, which is known as the salinity of ocean water. Salinity is expressed by the amount of salts dissolved. There are 47 different sea salts. Among the 47 salts, sodium chloride accounts for 77.8%. Salinity is the saltiness or dissolved salt content of a body of water. It is a general term used to describe the levels of different salts such as sodium chloride, magnesium and calcium sulfates and bicarbonates. The original definition of salinity was in terms of grams of dissolved salts per kilogram of seawater. Salinity is now defined in terms of seawater conductivity and is currently calibrated using a standard solution prepared at a laboratory in the UK. The technical term for saltiness in the ocean is salinity. In oceanography, it has been traditional to express salinity not as percent but as parts per thousand, which is approximately grams of salt per kilogram of solution. The quantity of dissolved salts, hence the salinity, affects seawater density, which also depends on temperature and pressure. Salinity and density share a positive relationship. As density increases, the amount of salts in the water, also known as salinity, increases. Various events can contribute to change in the density of seawater. Salinity can decrease from the melting of polar ice or increase from the freezing of polar ice. Evaporation increases salinity and density, while the addition of fresh water decreases both salinity and density. If the various specimens of seawater of different parts of the oceans and seas are considered, the ratio of the main salt is almost the same, but there is a variation in the salinity in them. Isohalogens are drawn on the sea surface or at a depth of water to express salinity. Isohalogen is an imaginary line drawn to join places having equal salinity. Next, we shall move on to temperature distribution in the ocean. Temperatures in the ocean decreases with increasing depth. There are no seasonal changes at greater depths. The temperature range extends from 30 degrees centigrade at the sea surface to -1 degree centigrade at the seabed. Like salinity, the temperature at depth is determined by the condition that the water encountered when it was last at the surface. In the low latitudes, the temperature change from top to bottom in the oceans is large. Vertically, the oceans can be divided into two reservoirs, a warm surface reservoir and a cold deep water reservoir. These two reservoirs are separated by a zone of rapidly changing temperature, which is referred to as the permanent thermocline. Above the permanent thermocline, the distribution of temperature with depth shows seasonal variations. In mid-latitudes, a seasonal thermocline often starts to develop in the spring above the permanent thermocline as surface temperature rise and mixing by wind is small. In summer, this seasonal thermocline reaches the maximum development. In places or during periods of extensive mixing, the mixed surface layer may extend to the permanent thermocline. The permanent thermocline is not found at high latitudes where the surface water are very cold and there is little variation in water temperature with depth. It is in these high latitude regions that cold surface water can sink to depth. This process is responsible for the vertical circulation of ocean waters called thermohaline circulation because density differences due to temperature and salinity differences are responsible for the circulation. Upwelling, the movement of deeper water towards the surface, and downwelling, movement of surface water to greater depth, are important processes in the ocean. Upwelling and downwelling can occur locally in coastal waters or on a large scale involving significant volumes of ocean water. During upwelling, deeper cold water is brought towards the surface and isotherms deflect upwards. During downwelling, warm surface water is moved to greater depths and isotherms are deflected downwards. The temperature of seawater is fixed at the sea surface by heat exchange with the atmosphere. The average incoming energy from the sun at the earth's surface is about 4 times higher at the equator than at the poles. The average infrared radiation heat loss to space is more constant with latitude. As a result, there is net input of heat to the earth's surface into the tropical regions, and this is where we find the warmest surface seawater. Heat is then transferred from low to high latitudes by winds in the atmosphere and by currents in the ocean. The geothermal heat flux from the interior of the earth is generally insignificant except in the vicinity of hydrothermal vents at spreading ridges and in relatively stagnant locations like the abyssal northern North Pacific. Water is transparent, so the radiation penetrates some distance below the surface. Heat is also carried to deeper levels by mixing. Due to the high specific heat of water, diurnal and seasonal temperature variations are relatively small compared to the variations on land. Oceanic temperature variations are on the order of a few degrees except in very shallow water. Most solar energy is absorbed within a few meters of the ocean surface, directly heating the surface water and providing the energy for photosynthesis by marine plants and algae. Shorter wavelengths penetrate deeper than longer wavelengths. Infrared radiation is the first to be absorbed, followed by red, and so on. Heat conduction by itself is extremely slow, so only a small proportion of heat is transferred downwards by this process. The main mechanism to transfer heat deeper is turbulent mixing by winds and waves, which establishes a mixed surface layer that can be as thick as 200 to 300 meters or even more at mid-latitudes in the open ocean in winter or less than 10 meters in sheltered coastal waters in summer. Now coming to salinity distribution in the ocean. Salinity is a seawater property related to the amount of salts dissolved in the water. The spatial distribution of sea surface salinity in the ocean is significantly different from the sea surface temperature. Global salinity patterns are linked to rainfall and evaporation. Salinity affects seawater density, which in turn governs ocean circulation and climate. Salinity variations are driven by precipitation, evaporation, runoff, and ice freezing and melting. The distribution of dissolved salts in the oceans and adjacent seas varies in space and time. Geographical variations in inputs create regional differences in salinity at the sea surface. As seawater circulates down into the ocean away from the sea surface, it carries these differences along, creating large-scale salinity patterns throughout the ocean. Changes in time in the inputs at the sea surface also affect the salinity distribution. The latitudinal distribution shows that there is a low salinity at the equator ranging from 34 to 35 parts per thousand because of high rainfall and the large number of days with overcast sky. The region between 20 to 40 degrees north and 10 to 30 degrees south are the region of high salinity due to large number of cloudless days, which increase heat and promotes evaporation. After obtaining maximum in the lower middle latitude, salinity again decreases to 31 parts per thousand in the northern hemisphere and 33 parts per thousand in southern hemisphere, that is 40 to 60 degree north and south. Further, poleward salinity decreases due to the melting of ice. The average salinity of northern hemisphere is 34 parts per thousand, while in south it is 35 parts per thousand. This is attributed to the fact that in the south a comparative less of mixing and less addition of fresh water takes place, and there is absence of land. There is an excess of fresh water at the mouths of rivers because rivers bring a lot of fresh water. In enclosed seas where the rivers bring fresh water and where there is an outlet into open seas, the salinity is low. The reason is that the salts brought by rivers get an opportunity to escape into wide sea. This reduces salinity. Where there is no outlet for the water to escape, then the salinity increases. Salinity either decreases or increases with depth according to the nature of water mass. Generally, there is a decrease with increase of depth. Generally, it can be said that in high latitude, salinity increases with depth due to denser water mass found at the bottom. Evaporation, precipitation, river water, temperature, atmospheric pressure, wind direction, and the movements of seawater are responsible in controlling the salinity. Higher rate of evaporation, as in the subtropical ocean, is resulting in high salinity. The high precipitation along the equatorial region reduces the salinity, therefore low salinity occurs. Similarly, large quantity of fresh water from melting of snow is added in the regions of Baltic Sea, thus reducing the salinity. When trade winds carry saline water away, upwelling of cold water reduce the salinity. The tides and the ocean current help in mixing of surface water, thus controlling the salinity. Ocean salinity would constantly increase unless there was a means for removing some of the minerals that are continually delivered. Removal mechanisms include deposition to the ocean floor and uptake by biological organisms. For example, shellfish and coral reef sequester enormous quantities of calcium that would otherwise dissolve in seawater. Next is environmental consideration. Salinity is an ecological factor of considerable importance, influencing the types of organisms that live in a body of water. As well, salinity influences the kinds of plants that will grow either in a water body or on land fed by water. A plant adapted to saline conditions is called a halophyte. Organisms that can live in very salt conditions are classified as halophiles. Specifically, an organism that can withstand a wide range of saltiness is euryhaline. The degree of salinity in oceans is a driver of the world's ocean circulation, where density changes due to both salinity and temperature changes at the surface of the ocean produces changes in buoyancy, which cause the sinking and rising of water masses. Changes in the salinity of the oceans are thought to contribute to global changes in carbon dioxide, as more saline waters are less soluble to carbon dioxide. In addition, during glacial periods, the hydrography is such that a possible cause of reduced circulation is the production of stratified oceans. Hence, it is difficult in this case to subduct water through the thermohaline circulation. A seasonal thermocline is formed when surface water is cooled and sinks to the bottom, resulting in a mixing of the layers. The approaching cool weather impacts primary production in the euphotic zone by cooling the surface water and bringing phytoplankton with nutrients to the creatures below. Shorter days and lower angles of sunlight limit the growth rate of the phytoplankton, which in turn limits the primary production and growth rate of organisms higher on the food chain. A new thermocline is created in the spring when the increase in sunlight results in less mixing and a bloom in phytoplankton. The waters turn from blue to green as the increase in the number of phytoplankton dissolving inorganic nutrients causes an increase in chlorophyll biomass. Herbivores' zooplankton biomass also begins to increase, providing food for an entire food web above that depend on the energy they provide. During the summer, the phytoplanktons absorb most of the dissolved inorganic nutrients from the surface water and are consumed by the zooplankton, decreasing the rate of photosynthesis. Vertical mixing ceases and phytoplankton, which remain in the upper layers, become nutrient limited. The cycle starts all over in the fall when the surface water cools, churning the deeper nutrient-rich water into the depleted surface waters. Nutrients become available again and phytoplankton blooms in great quantity during the spring after the intense winter mixing. The seasonal cycle of phytoplankton growth is an amazing demonstration of the complex and interwoven physical, chemical and biological processes of the ocean. As climate change has warmed the earth, oceans have responded more slowly than land environments. But scientific research is finding that marine ecosystems can be far more sensitive to even the most modest temperature change. Global warming caused by human activities that emit heat-trapping carbon dioxide has raised the average global temperature by about 0.6 degree over the past century. In the oceans, this change has only been about 0.1 degree centigrade. This warming has occurred from the surface to a depth of about 2,300 feet, where most marine life thrives. Perhaps the ocean organism most vulnerable to temperature change in corals. There is evidence that a reef will bleach at even a slight persistent temperature rise. Bleaching slows coral growth, making them susceptible to disease and can lead to large-scale reef die-off. Other organisms affected by temperature change include krill, an extremely important link at the base of the food chain. This can have a cascading effect by disrupting the life cycle of krill eaters such as penguins and seals, which in turn causes food shortages for higher predators. We are already facing the effects of higher ocean temperatures in the form of stronger and more frequent tropical storms and hurricanes or cyclones. Warmer surface water dissipates more readily into vapor, making it easier for small ocean storms to escalate into larger, more powerful systems. These stronger storms can increase damage to human structure when they make landfall. They can also harm marine ecosystems like coral reefs and kelp forests. And an increase in storm frequency means less time for these sensitive habitats to recover. We can conclude this session. The temperature and salinity of the ocean varies from place to place and from season to season. Ocean temperature depends on the amount of solar energy absorbed. Much of the ocean has salinity between 34 parts per thousand and 36 parts per thousand, but there are places that tend to be higher or lower. However, the effect is greater if the salty water gets cold, as temperature has a greater effect on density than salinity does. A combination of high salinity and low temperature makes seawater so dense that it sinks to the bottom of the ocean and flows across ocean basins as deep, slow currents. So students, thank you very much for watching this episode. Hope we will meet in the next session. Until then, take care. Thank you.